Yeah, I'm going to hand back to Luis Torres Cruz, and he's going to talk to us about laboratory testing, CPTU-based charts. So welcome back, Luis. Over to you.
Thank you, Andrew. Okay. So this presentation is based on section 6.3 of the bulletin, which deals with laboratory and in situ testing. The objective is to provide an overview of the main challenges and methods of laboratory and in situ testing of tailings. So let's start with some of the challenges that are pointed out in the bulletin. One of them is that when it comes to conventional unthickened tailings deposition, particle segregation will induce heterogeneity in particle size distribution. So it means that, for instance, sorry, let me change my pointer option here. If we take samples starting at the point of deposition and we move progressively towards the pond, because the coarser particles settle out of the slurry first, we should expect to see coarser particles over here close to the point of deposition than over here closer to the points. And well, closer to the pond. And of course, that's not only an expectation, that is actually what you see. And for this reference that I'm showing on the slide, this was done along 3 alignments. And for all 3 of them, one sees a reduction in the average particle size as you get away from the point of deposition. Now, of course, it's not a neat or monotonous reduction in particle size. However, over a distance of, let's say, 60 meters, the trend does emerge. This also has implications on vertical variability, because not only do you get a particle size distributions that are finer as you move away from your point of deposition, but also you find finer particles as you go down into the deposit, because this point over here is farther away from the point of deposition than this one over here is from its own point of deposition. So again, that is an expectation that we actually see reflected in experimental data, as shown over here in this figure on the right-hand side. This is figures from the Jeff Blight's book on geotechnical engineering of mine waste storage facilities, and he is showing the role of thickening. So when dealing with slurry type deposition, where there has not been any thickening performed on the tailings, you see that particle segregation, but you do not see it, however, when you are dealing with thickened, dewatered tailings. So in that case, there will be a negligible change in particle size distribution. Another aspect that complicates the characterization of the tailings is that unthickened tailings will be found most often in a highly interbedded structure. And we really mean highly here. So in the previous figures, I was showing differences in particle size distribution that might occur when you go from one point to another, that is, say, a few meters away. But also that fluctuation in particle size distribution can occur in the scale of centimeters, right? So if one extracts a sample of tailings, you will observe that intense layering. And I'm showing a few examples here in these figures, the 2 on the left from South Africa and this one over here on the right from the Brumadinho Dam in Brazil. And I want to bring to your attention, this scale over here is centimeters. This one over here is centimeters. From this point to this point, that is half a meter. And over here, we have fingers for scales, so showing us that these layers can really be as thin as only a few millimeters in some cases. Moving on to determination of the critical state line, some of you might know that a couple of years ago, David Reed and Andy Fourie ran this round robin exercise in which they took a sample of tailings and they sent a sample of the same tailings to several geotechnical laboratories around the world, and each laboratory was to measure the critical state line of those tailings. And the idea was then to compare whether everyone was arriving at the same critical state line or not. So this was a massive undertaking. And the results, I think, are very interesting. I mean, I must say it's the only exercise of its kind that for critical state line that I am aware of. So here I'm showing a summary of the results. On the left-hand side, we see void ratio versus mean effective stress. So let's call this the state plane. And over here on the right-hand side, we have the deviator stress versus the mean effective stress, the stress plane. And we have the data from all the laboratories in both planes. So it is interesting that over here on the state plane, the scatter is much more obvious than over here on the stress plane. Over here, all the labs produce data that agrees quite well. All the data points are very close to this line of Q equal to 1.4 P prime. Not so much over here, where the data fall on a band that has a width in terms of void ratio of 0.1. That is significant scatter. So the data from the laboratories over here, it is defining a critical state line, but over here it's defining sort of like a critical state band or a critical state swath, we may call it. So why is it? Why is it that we get such good convergence over here on the right-hand side, but we don't see that convergence over here? I believe the conclusion that one has to draw from this is that the key to getting a reproducible critical state line is proper measurement of the void ratio, because the void ratio is not involved over here. So long as the labs don't have to measure the void ratio, they can all agree, right? But once you bring in the void ratio, that's where the scatter starts becoming more apparent. So careful measurement of the void ratio is crucial when obtaining reliable measurements of the critical state line. So what can one do to get good measurements of the void ratio? Let's have a look at some suggestions. So firstly, we need to make sure that we define our critical state line using contractive specimens. In other words, loose specimens. Why contractive specimens? Why not dilatant ones? Since dilatant ones will also reach the critical state line. Yes, the critical state line is applicable both to dilatant and contractive specimens. That is correct. However, dilatant specimens are prone to strain localization, meaning that the void ratio along the failure plane, as we can see from this computed tomography image, the void ratio along the failure plane will be different than the void ratio in the remainder of the specimen. And in the laboratory, what we can measure will be the overall void ratio of the specimen. We cannot isolate, not in a traditional laboratory certainly, we cannot isolate this shear band to measure the void ratio only there. So the recommendation to use contractive specimens is geared towards avoiding this type of strain localization. The second suggestion is to keep in mind that the critical state line is independent of the sample preparation method. In other words, of the method that you use to reconstitute the specimen in the laboratory. Accordingly, one should try to use the method that allows the best control over the initial or preparation void ratio. And generally, that is regarded to be the moist tamping method. So setting up for careful execution of moist tamping does require investing a little bit in time and machining a few tools that will allow you to carefully control the height of the different layers that you're going to moist tamp. And I'm showing here an example of tools that you can use to control the moist tamping procedure. These are not tools that I have found to be commercially available, so one has to request them to be machined for the purpose. But I do think they go a long way in helping you ensure that you can consistently apply the moist tamping method. I also want to highlight here that when you use the moist tamping method, you have very good control of the void ratio that your specimen is going to achieve at this point. This specimen right there is mounted on the base of the triaxial cell, right? It has a porous stone at the bottom, another one at the top, and through the moist tamping method, we have a very good control of the void ratio as it exists right there. This is different from the void ratio that this specimen is going to exhibit at the beginning of the triaxial test. Why? Because this specimen here is not saturated. The tailings, in this case, they are moist, as the name moist tamping suggests, but it is not saturated. So you still have to saturate this specimen, and then you have to consolidate it to the pressure level that you are interested in. And during that saturation process and during the consolidation process, there are going to be changes in void ratio that are impossible to control and even difficult to predict. So while the moist tamping method gives you control over your preparation void ratio, it doesn't give you control over the void ratio that the specimen is going to attain at the beginning of the triaxial test. Now, for those of you that are more familiar with laboratory techniques, you will know that sometimes there is an under compaction technique that is used because you are compacting the different layers, right? So the idea with the under compaction technique is that you don't want the bottom layer to end up being more compacted than the layer at the top, because the bottom layer you compact it once when you set it up, and then again when you set up the layer on top of it, and then again every time that you put a new layer, right? So there are some under compaction techniques to account for that. However, the data from the round robin experiment or exercise suggests that under compaction does not really affect the results, and that also there is no magic number of layers that we have to be used. The CSLs that resulted from this round robin exercise were also not influenced by the number of layers that the different laboratories used. Point number 3 is that generally undrained tests are useful to define the critical state line at low values of the mean effective stress, P prime, whereas drain tests help define the CSL at large values of P prime. So we can see that here nicely illustrated in this figure. This test right here is giving us the value of the, or a point on the CSL at a P prime of approximately 15. This one here at approximately 50. This one here is at approximately 150. Let's say it's a bit tricky because of the logarithmic scale, right? And we know that these 3 tests are undrained. We know that they are undrained because they moved only horizontally at a constant void ratio. And that's what happens during an undrained test. The void ratio is not allowed to change. This one over here, on the other hand, we know that it is drained because the void ratio did change during the test. It went from being in this position to being in this position over here with a P prime value of approximately 700 kilopascals. So this final P prime value of 700 kilopascals would be very difficult to achieve with an undrained test. So you would have to put your initial condition, let's say over here, so that it reached this value. So you may easily have to consolidate to more than 1000 kilopascals. And at those stress levels, some laboratory equipment might struggle to reach those values of P prime. The other thing that I want to bring to your attention, which I think we're not always aware of, is that, say for instance, that you already have these 4 points for this critical state line. At this point, you might be thinking that it would be very nice if we could have another point over here so as to have a uniform distribution of our points in the critical state line. It would be quite convenient if we had a test that reached a critical state at a P prime. Let's see, this is 100, 200, 300, 400 of 400 kilopascals. So what can you do to set up a test that will actually reach a critical state P prime of 400 kilopascals? That's also, to answer that type of question, you use a drain test, right? So drain tests are also very useful for that, okay? And the thing is, with a drained test, you know what your effective stress path is going to look like, right? Typically, it's going to have this slope of 3, and you know that it is going to approach your critical state line. And because at this point, let me go back one slide, because at this point, you already have 4 points, right? Then you have a good idea of what is the slope of your critical state line in Q versus P prime space. So you know that if you want to reach this point over here, which in this case would be 400 kilopascals, then that is going to inform which is the initial value of P prime at which you need to set up your triaxial test. And this is the equation that you can use to calculate it, right? So that's your initial value of P prime that you need to set up to reach this critical state value of P prime. So this would be the 400 kilopascals in our case. And this M would be the slope of your critical state line in your Q versus P prime space. The fourth point is that for void ratio determinations, you need to determine the end of test water content of the specimen by freezing or squeezing. There is no alternative to this. There is no way of reliably determining the critical state void ratio based only on the dimensions of the specimen. It does not work. I have not seen it work once. The only way of making a reliable estimate of the void ratio at critical state is if at the end of the test, you determine the water content of the specimen, and then you calculate your void ratio based on that water content of the specimen. And well, how do you calculate the water content of the specimen? You have two options: freezing or squeezing. Okay, and or actually there, I guess you have a third option. You could do both. You could first squeeze and then freeze, right? So the details of the freezing procedure are given in Appendix B of the soil liquefaction book by Jeffries and Bean. So it is described there in quite some detail. Now, I know that some laboratories are reluctant to implement this method because it means that they have to make some adjustments to their triaxial cells so that they are not damaged when they, not so much to the cell, but to the base of the cell, so that they are not damaged when they are put in the freezer. So but that's okay, because you can also do the squeezing procedure, right? Which was first described by 1996. And guys, you will have to excuse here the shameless self-promotion, but I did describe it in quite some detail in my thesis, and I added some figures there that I think would be useful for anyone trying to implement this in the laboratory. So I'm adding the reference to my thesis there. Now, in the round robin exercise for the CSL, the authors point out that the laboratories using end of test soil freezing produced the most consistent definitions of the critical state line. So I think that this result gives the impression that therefore freezing is going to be like the optimal method. The reason why I do not believe that this is necessarily the case boils down to this figure right here, okay, which is from a 1996 paper in which the authors used the squeezing method to determine the void ratio. And what I want to bring to your attention is the remarkably well-defined critical state line that they obtained. Okay, there is very little scatter here. They called it the steady state line, but of course, same thing. So this is what this is my basis to say, look, if the squeezing method works as well as, yes, the squeezing method works as well as anything that one, as anything else that one might use. Okay, in other words, works as well as the freezing method. The other thing that I would like you to keep in mind is that not all critical state lines are equally reliable, and this is particularly important when considering the void ratio versus P prime projection. Oftentimes we're going to have the points right in this plane, and then you're going to do your best fit, and you're going to use that best fit to get a value of gamma and to get a value of lambda, and that's it. However, we lose sight of the fact that that best fit is based on these points, and that those points have a certain level of scatter, and that scatter affects the confidence that we can have on the value of lambda and gamma that we obtain from the best fit. So for example, I am showing here data points that define two critical state lines. We have these points over here at the top, the circular markers, and we have these points over here at the bottom, the squared markers. It is clear that the points at the top have much more scatter than the points over here at the bottom, and that therefore we can trust this critical state line here at the bottom. We can trust it more than this one at the top. Okay, that is, let's say, at an intuitive level. But you can quantify that. You can quantify the standard error of the slope and of the y-intercept given the scatter of the underlying points. And that's what we see in this figure. Okay, so this is showing us the normalized standard error of the slope versus the normalized standard error of the intercept, which I've been calling gamma 100. And this is based on a database of over 150 non-plastic soils reported in the literature. Now, again, I think this is a useful tool to do a bit of quality control on your data. Once you have the data points that are defining a critical state line, you may be asking yourself, well, is this level of scatter reasonable or not? And to answer that question, you can plot the normalized standard error of your slope and the normalized standard error of the intercept in a chart such as this one, and see where your scatter falls. So the further up and to the right that your data falls, it means the higher the scatter. So ideally, you want to be somewhere over here. There are no solid boundaries here between what is acceptable and what is unacceptable. But all I can say is this is all published data from the technical literature. So if you are in the bulk of the data, then I think you can rest easy. Right. And the other thing that I wanted to say is that then the equations to calculate this normalized standard error, either for the slope or for gamma, are given here in the reference at the bottom. Moving on to in situ testing. Just want to check how I'm doing with time. Okay. Moving on to in situ testing, the bulletin points out that the CPT is widely agreed to be the most reliable, repeatable, and versatile means available to characterize in situ behavior. Okay, and we have all seen this in everyday experience, but it's also important to be aware that significant uncertainties remain in the interpretation of the CPT, and I hope to make that clear towards the end of my presentation. But before I do that, I want to show you some charts that I have found useful in interpreting CPT data. So these are sometimes referred to as soil behavior type charts based on CPT data. So essentially what these charts do is that they have two axes, right? And each axis is a parameter that depends on the results of the CPT sounding. And then the chart is divided into different areas that correspond into different types of soil behavior. And by soil behavior, that term is maybe a little bit vague because it can mean two things. It can mean, well, what type of soil is it? So is it sand-like, or is it behaving like a silt, or is it behaving like a clay? But it can also mean, is it contractive or dilatant? And I will show you some examples. So this chart that I'm showing in this slide is from a 2017 publication, and I find it quite useful because it is applicable regardless of the saturation level. So this chart works for, or at least is intended for, both saturated and partially saturated soils. It's not as well known as other charts, so I wanted to bring it to your attention here. Then there's also this chart published in 2008 by Schneider and his co-authors, and it has become quite popular in the last few years. And the authors explain that in developing this chart, the emphasis was on determining whether the penetration was drained or undrained or partially drained. So here we have the chart divided into these different areas. So over here in this blue area, if your data plot over here, then the authors are telling us it means that the CPT was drained. However, if your data plots over here, it means that your soil is behaving as a clay, and therefore the CPT was undrained. And what happens if your data plots over here in the white area? Well, it can mean different things. If it plots over here, it means that your soil is partially drained. So there is some development of excess pore water pressure, but also some dissipation. And that this is quite common for non-plastic tailings. And if it plots over here, your data might be indicating that the penetration was undrained or it was partially drained. Okay, so this is the Schneider et al. 2008 chart. And based on that chart, which I'm still showing over here, in 2022, we proposed a small modification to this chart so as to model these boundaries by contours of the parameter BQ. The parameter BQ is defined right here, and it is essentially the excess pore water pressure normalized by the tip resistance. So what we are saying in this chart is that these boundaries can be approximated by contours of BQ such as 1, 0.6, 0.2, 0.05, and 0.01. So we are suggesting that this blue area is considered to be drained. This brown area over here is considered to be undrained, and this white area can be partially drained or undrained. A chart that has become quite common is this one proposed by or illustrated in the Jeffries and Bean soil liquefaction book, right? They use contours of this parameter called IC, right? And depending on what is your value of IC, then you are dealing at a soil that is behaving like dealing with a soil that is behaving like a gravelly sand, a clean sand, or sand-silt mixtures, and so on. And this is the equation for these contours of IC. So the soil behavior type index, in this case IC, will always be a function of the parameters plotted along the two axes of the chart. So in this case, we can see that IC is a function of Q prime, and Q prime is simply this parameter over here, okay, and of F, which is the friction ratio over here. And I should point out that Q prime, which is often expressed as we see here in this equation, right? We see that expression over here. If you do the arithmetic with these of this expression here, this is what you're going to arrive at. So this is essentially like a normalized effective tip resistance. And I say effective tip resistance because it is the tip resistance minus the pore water pressure. And by the way, my apologies, there should be a sub index here, U sub 2. Okay, so this is the tip resistance minus U sub 2, that's the dynamic pore water pressure measured at the shoulder, divided by the vertical effective stress. Okay. And the nice thing of having these soil behavior type indices, such as IC as defined by Bean and Jeffries, or BQ as I showed you for that you can use on the Schneider chart. There's also a version of IC that was proposed by Robertson and Ride. And there are other indices proposed in the literature. Well, anyway, the nice thing of these indices is that it allows you to plot profiles of soil type, so that you can see how your soil type is changing as you go deeper into the ground. The chart that is proposed by Bean and Jeffries, this one that has a space of Q prime versus F, it can also be combined with what is known as the Pluis method, right? And the Pluis method is a method that is a method that aims at giving you an estimate of the state parameter psi. And you will recall from my first presentation, this state parameter psi is the one that is telling us whether the soil is contractive or dilative. And this has important implications on the stability of a soil. So, or rather on the stability of a dam. So if you follow the Pluis method, right, you can plot contour lines of the state parameter on this chart, right? Meaning that if you have your CPT data and you can calculate this Q prime and your F, then you can also calculate what is the state parameter of that soil. And I want to bring to your attention some of the quotes in the Jeffries and Bean soil liquefaction book about the Pluis method, right? So they say, for example, that the Pluis method is a screening level evaluation that has been found to be surprisingly accurate in estimating the state parameter. It also says that the Pluis method is a very useful method for a first look at the data and is often quite accurate. This method, again I'm quoting, this method is based on Pluis et al. And experience across many sites suggests that it is surprisingly accurate. So of course you read all these statements and you have to arrive at the conclusion that the Pluis method is quite accurate, okay? And we have to be very careful with that conclusion. So for example, this Pluis method uses a correlation. So it requires the slope lambda of the critical state line. And to calculate that lambda, it uses a correlation with the friction ratio of the CPT. This is what I am referring to. This is the graph in the original Pluis method paper showing the correlation between lambda and the friction ratio F. And with the data that was available at that time, it appeared that it was a reasonable assumption to say that lambda is simply the friction ratio divided by 10, right? As simple as that. If your friction ratio was 1, then your lambda was 0.1. However, this was back in 1992. And since then, more and more data became available. Here on the right-hand side, I am showing a compilation of data published in 2021, okay? And the more data we collect, two things we have to say. Firstly, that the data continues to cluster around the initial correlation, okay? So that is a good thing. However, the second thing that we have to notice is that the scatter is quite significant. So for example, if your friction ratio is anywhere between 0.4 and 1.3, then your lambda, what the data is saying is that lambda can be anywhere between 0.03 and 0.18. So from 0.03 to 0.18, that is a range of 0.15. How big a range is that? Well, it depends. What is the total range of values of lambda that non-plastic soils can have? Let's say in the case of tailings, what sort of values of lambda can we expect to see in tailings? What values are credible? Well, as a lower bound, just to simplify things, we can say that lambda can be as low as 0. Okay, of course, it's never going to be 0, but let's just assume that it is 0. And how high can it go? The data shows us that values of lambda in non-plastic soils can go as high as 0.3. Okay, that's a bit of a push, but let's accept that. So the credible range of values goes from 0 to 0.3. And this level of uncertainty here has a range of 0.15. In other words, it's the uncertainty is half of the credible range of values that we can expect to see. Let me put it this way. If we assume that the life expectancy of an average human being is 80 years, then this would be like trying to guess someone's age with a error margin of plus minus 20 years, right? This is as if someone were to say right now that they believe that my age is somewhere between 20 and 60 years old. Like, yeah, they would be right, but it's not a particularly impressive estimate. So there's considerable uncertainty there. Okay. Furthermore, I mean, clearly I take issue with this, right? So much so that I dedicated an entire paper to warning about the uncertainty of the Pluis method. And my conclusion in that paper is that the uncertainty of the method is too high for detailed estimates of the state parameter. Okay, so there is no data, none whatsoever, to suggest otherwise. Okay. And I am not the only person saying this. We see this paper from 2007 from Don Shuttle and John Cunning. They point out some initial steps for evaluating the CPT in silt have been presented by, among others, Pluis et al. 1992. That is the Pluis method. Okay, but these methods might be argued as speculative. Okay, so we have gone now from surprisingly accurate to speculative. Please keep that in mind. Now I'm going to show you the chart proposed by Peter Robertson. Again, it is based on CPT results. So there's a lot of information packed into this chart. So let's break it down. So the first thing that I want to ask you is to please ignore these dashed lines in the background. Those dashed lines correspond to an earlier version of a chart by Peter Robertson, and he included them here in this figure just for comparison purposes, but they play no role in the interpretation. So this chart is divided in two ways. The first way is that it is divided depending on whether the CPT is expected to be drained, that would be the blue area, undrained, that would be the brown area, or partially drained, that would be this white area over here in the middle. And the second way in which the chart is divided is into whether the soil is dilatant. That would be this green area over here. Okay, and that's, by the way, that's why you see all these areas are labeled with a D as the second letter, right? Sand-like dilatant, transitional dilatant, clay-like dilatant, right? Or whether the soil is expected to be contractive, and this area over here being an area of uncertainty. And these are this is rather the suite of 3 charts that Peter Robertson suggests for assessment of the condition of the state of the soils, including tailings. And I want to bring your attention this one over here, which uses shear wave velocity to assess whether there is any cementation between the soil particles. I have found this reference to be very useful. It provides a very thorough description of different types of soil behavior type charts. In particular, if you're interested in this, please have a look at Appendix A. And another thing that I think enhances the usability of this document is that it includes supporting spreadsheets. The whole thing is freely available at this link that you see on the slide. Now, coming towards the end of the presentation and returning to this topic of the uncertainty around CPT interpretation, again, I want to touch on assessments of the state parameter, because this is clearly something that is very relevant to tailings engineering. So on this slide, I am showing the reports into the failures of different tailings dams. So this reference here, Morgenstern et al. 2016, is the failure report into the Fundão tailings dam. This one into Cadia, and the last 2 into the Brumadinho dam failure. And I am highlighting over here the references that were used in each report to try and assess the state of the tailings using results from the cone penetration test. And by state, I mean to try to assess whether the tailings were contractive or dilative. And I have highlighted those references that focus on determining the state parameter. And you can see that there are quite a few references highlighted. We could say that most of them have been highlighted. In other words, most of them are focused on determining the state parameter. So clearly, we have a lot riding on this idea, on this possibility of determining the state parameter using the results from the CPT. So we should be asking ourselves, well, can we determine the state parameter of loose tailings using the CPT? So let's explore that question a little bit. Sometimes the answer to that question tends to be yes, the method has been validated, and there's data, for example, in this reference from 2008 that shows that if you take the state parameter calculated using the widget method, right, and you compare it to the state parameter that was actually measured in the soil, the data aligns or clusters around the identity line, meaning that the calculated state parameter was equal to the measured state parameter. But there are several problems with this figure as a validation of our ability to measure the state parameter from the CPT. The first problem is that this was not this data does not come from actual tailings deposits, but rather it comes from calibration chambers. Calibration chambers where you know the horizontal stress level. In a real tailings deposit, you don't know it. Calibration chambers where you have a uniform deposit of sand. You don't have that layering that we saw earlier. And also, this is all sands where all the CPTs would have been fully drained. We don't have that in our tailings. And more importantly, when we're doing tailings engineering, very often we're interested in the looser tailings, those that have a state parameter that is positive. However, the database over here is dominated widely by dense sands, those that have a negative state parameter. And at the end of the day, what really matters is if your prediction is matching the experimental measurement. Is your prediction matching the observation? So we published this figure in a 2022 paper where we showed the state parameter as inferred from the Jeffries and Shuttle and collaborators widget, okay, and which is regarded as the, let's say, as the most advanced method to infer the state parameter. And we compare it to the state parameter that was actually measured in the samples. And here's your identity line. And we can see that the data does not cluster around that identity line. We concluded that the figure is a reminder that the validation of the widget method in real silt deposits is a pending task for the geotechnical community. And I think that sometimes we lose sight of that, okay? And we believe that, oh yeah, we need the state parameter, we do the widget, it works. Well, no, the validation of the method is actually a pending task. Okay. More recently, other groups have continued to work on this, and here I'm showing data from this 2023 paper. And by continuing to modify the method, they achieve an improved match between the predicted state parameter, or the state parameter inferred from the CPT, and the state parameter measured in the sample. However, the authors, right, do not hesitate in pointing out that further work in these areas is needed, and I find it difficult to disagree with that. Okay, and with that, I come to the end of my presentation, and again, I thank you for your attention.
So yeah, I'm going to talk about measurement of undrained strength using in-situ tests. It's fairly rudimentary. I think the target or the aim of today's sessions were to kind of bring people up to speed. I'm not aiming this at the world experts in the audience, because there's a lot of basic stuff to get through. Some of the terms and the equations and so on that Louis showed, I'll kind of step through those a bit more slowly, and also just talk about the various measurements that are made during the in-situ tests. So fill in some of that background perhaps. The workhorse of the in-situ testing industry is the CPT, clearly, and that's where we'll spend most of our time in this session. But I will talk about field vein tests, and then some of the other penetrometer types that are being trialed, but very much in the kind of proof of concept stage, I guess. And I'll talk about those at the end. Just before I get onto the CPT, I'm focusing just on one aspect here. That's the undrained shear strength. You see lots of correlations with CPT data, with all sorts of other things, and so people show correlations with friction angle, with undrained Young's modulus. They can probably even predict who's going to win the next American election. There seems to be no limit to what people think you can get from a CPT. I'm a little bit skeptical about many of those things. I think it's kind of stretching it just a bit too far. Again, I suppose if you take it at the sort of condition that it's maybe a rough empirical correlation. But I see too many reports where people are taking things as gospel, these correlations. Undrained strength has probably been tried and evaluated in far more detail and far more commonly, so perhaps I feel a bit more comfortable with that. So I'll talk about the CPT, the cone penetration test. Within that, I'll talk about dissipation tests and how important those are, and then link that to field vein tests, and then talk pretty briefly about these full flow penetrometers. So the CPT test, as I said, it's kind of our go-to type of method. When you see that little subscript u, lowercase u, it usually indicates that it's a CPT that actually includes a pore pressure transducer. So in the early days, the CPT was just a tip resistance and a friction sleeve. And that seemed to suffice in cases where people kind of knew the material they were testing, such as the sand. They were kind of just interested in tip resistance. It was being used for things like foundation loads, etc., etc. However, now, these days, it would be kind of criminal to do without the piezometer component, particularly in tailings work. Now, the standard is to use this rate of 20 millimeters a second. Why? Well, I guess, and this comes to some of the other discussion we might have a bit later, where I think perhaps traditional soil mechanics, undergraduate soil mechanics, we have sands and then we have clays, and never the two shall meet. So sands behave drained, and clays behave undrained, and that's it. So this concept that a sand can behave in an undrained way was kind of anathema to a lot of geotechnical engineers. When we started running our static liquefaction workshops, I think the first was 2017, we had a lot of pushback from people saying, but everybody knows sand can't fail in an undrained fashion. Well, I think most people have now been converted to the new religion where, in fact, you recognize that in certain circumstances, it certainly can. And I think, and I haven't looked at this in any detail, people that are more familiar with CPT testing might confirm this, is that I think that rate of 20 millimeters a second probably gives you drained behavior in a sand and undrained behavior in a clay. The trouble is tailings don't fit that kind of categorization that easily or that often. And we'll come to that. Now, when we're using a proper CPTU, there's typically 3 independent data channels. There's the tip resistance. Now, you need to correct for that measured tip resistance or the load. So, and again, in the literature, it's kind of all mixed up often. But uncorrected, it's often referred to as Q subscript C. Once it's been corrected, Q subscript T. But you will see the QC used sometimes for when it's corrected. Usually the CPT contractor will have done that correction. It's just because there's a little bit of a pressure effect on the back of the shoulder of the CPT that needs to be accounted for. It's worth just checking with your contractor, is this corrected or uncorrected? Because basically, if you're not doing that, you're starting off with a flawed piece of data already. So you get the tip resistance corrected, QT, the sleeve friction, and the pore pressure. These are the 3 things that we measure. So very simple illustration. Often you have a big rig, you have operators sitting inside the rig so they can do it in any kind of weather, and you're pushing this cone at this constant rate of 20 millimeters a second. Now, of course, the cone rods are only 1 meter long, so you have to keep stopping, disconnecting, reconnecting the next rod, and then starting to push again. So it's not as though you're pushing this entire available rod in one go, because it just wouldn't, would not be physically feasible. So as we're pushing, and I'm going to try and avoid using the pointer because only one screen shows up, and the poor people online have no idea what you're pointing at. And unfortunately, this device doesn't allow me to use the laser pointer option on the screen. So I'll try and avoid pointing as much as possible and rather just describing So you've got at the tip, you've got those red arrows, the arrows facing vertically upwards, and that's another thing I have to be careful of. Apparently, people who are moderately colorblind sometimes can't distinguish red from green, so I've got to try and keep that in mind as well. So at the tip, you've got this resistance, that's the tip resistance. You've got the arrows on the side of the shaft, that's the sleeve friction that you're measuring, and then you've got this pore pressure. Now, there was a lot of debate in the early stages, where do you measure that pore pressure? We've settled on just behind the shoulder, that blue, and hopefully people can see blue. That's where we measure pore pressure, and it's called the U2. That's where the U2 comes. It's got nothing to do with Bono, it's just the measurement where we make the pore pressure measurement. Just note that we're not measuring the tip resistance and the sleeve friction at exactly the same depth. There's a bit of an offset. Always keep that in mind as well. Here's a typical good quality cone. You'll see the white is the pore pressure, or the ceramic through which we measure the pore pressure at this position U2. There was on the face of the cone, people used this U1, but that's now been kind of consigned to history. That's a really good quality cone. You've seen on occasion the cone gets quite worn on perhaps one side. Just if you're in the field, you have the opportunity to inspect the cone, because if that happens, you can start getting the cone deviating from the vertical when you're penetrating. And then you kind of think you're measuring vertically and you're measuring at 45 degrees. These days, most contractors have an inclinometer, so they can ascertain they are pushing vertically. There's some classic photographs of, in early days in Holland, people pushing a cone in, and the motor car 10 meters away is being lifted off the ground, because the cone has done a complete 180 and come up under the car and pushing it up. So trying to avoid that. So we get this three channels of data. It's continuous. That's the wonderful thing about it. It's absolutely continuous with depth. And there's not many devices that do that kind of thing. In that sense, it's way better than, let's say, an SPT, where you're getting one channel, if you like, and it's also kind of intermittent. So we get this continuous measurement of these three channels of data. The photograph on the left is one of these large truck-like vehicles that, and you need a reaction to push against with the cone, because you're actually often generating a lot of resistance. So you need to keep that, the ability to push that cone. But sometimes you might be in really soft material. So the photograph on the right is like some kind of swamp buggy. And you can have contractors who can supply this kind of equipment. So you can get right out onto really, really soft tailings, perhaps even push through the decant pond areas if you really wanted to. So there's a whole range of options in terms of the kind of gear that's available. This is from some work published by Jeffries and Bean showing tests done in the same spot but at different times, showing the repeatability. So what they've got there is a plot with depth of the corrected cone tip resistance. The beauty of it is that you can probe to reasonable depth in a relatively short time. If the contractors are proficient, they're swapping the cones out regularly, you can get pretty good turnaround in terms of the CPT. So here's an example. So on the left, you've got tip resistance. The second from left is the friction sleeve. The next one is the friction ratio. And then one that's probably worth just dwelling on for a second is the pore pressure. So you get that normal, highly variable plot that you're seeing there. But that needs to be taken in comparison to the equilibrium pore pressure, which is shown as that very thin solid line that's kind of almost linear, I think, which is in this case your hydrostatic pore pressure. And this side is probably quite useful. They know where the groundwater table is, so you've straight away got one point on that line, and probably by doing a few dissipation tests to an adequate degree of dissipation, they could determine the actual equilibrium pore pressure at many other depths. But what we're measuring with the CPT is what effectively the dynamic pore pressure. So that U2 measurement is the dynamic pore pressure. So in this case, it's significantly positive. You can see as you're pushing, you're getting positive excess pore pressures. That's not always the case. In dense dilative materials, you push the CPT, you'll be getting negative excess, if that makes sense. Pore pressure. You're getting pore pressures less than hydrostatic. When you're allowed to dissipate, it'll go back to hydrostatic. So now we really need to know what that equilibrium pore pressure profile is, as I'll discuss in a few slides' time. Because we use that to do some of these normalization calculations that are required. You'll see that on the left-hand curve, or the left-hand graph, you've got the tip resistance. There's clearly a layer of significant strength. But then down below, it's pretty disconcertingly low, the tip resistances. Those are in megapascals. When you start having to plot your curve or your graph with kilopascals as your horizontal axis, you know you're probably in trouble, because then you're getting really small tip resistances. And sometimes that's obscured. People plot it in terms of megapascals, and they miss out what's happening. You know, they're at about 15 meters. There's really low values below the water table. So now the thing is, this tip resistance is a function of a number of soil properties. It's not just, we're not measuring anything directly. When we do a laboratory test, like a triaxial test, you're measuring sigma 1 and sigma 3. You know what they are. You know what the effective values are. You can calculate the shear strength really accurately. It's almost a direct measurement. Tip resistance is not. There's many other things influencing it. So that on its own is usually not enough to determine undrained shear strength, because remember, that's what you're talking about here. We need to measure the pore water pressure as well, and we use these normalization procedures. So here we go. These are the ones that Louis was using. You've got the normalized tip resistance. There you use the corrected value of the actual measured tip resistance minus the total vertical stress divided by the effective vertical stress. Sometimes people work in terms of mean stresses, but we then need to know what K0 is, which is another whole dilemma. So let's stick to the vertical effective stress. The friction ratio is just the measured skin friction divided by the tip resistance minus sigma V0. And the BQ parameter that Louis was talking about takes that U2 parameter, the dynamic or the excess pore pressure, minus your equilibrium, divided again by that QT minus sigma V, which can be expressed as delta U over that term. So these are these normalized parameters that we use. Now, periodically, during a penetration test, the contractor will stop the penetration and let that excess pore pressure decay. So if it's positive, it'll go back to, it'll come down. If it was negative originally, it'll go up. These, I think, are absolutely crucial to any CPTU investigation. Now, I do see it kind of an overuse, where people are doing it at every meter. I've never understood the need for that. I think often you do one CPT and you kind of determine where you want to do the dissipation tests in future, because there might be a layer that's clearly really low tip resistance. So you might pick a few points for doing your dissipation tests. They can be quite time consuming, so why would you do it every meter if it's not necessary? The thing is, we don't always have hydrostatic conditions, so the dissipation tests are essential to try and determine, well, do we actually have perhaps downward drainage? Because you've got an under drainage system that's functioning really well. So your pore pressure might be higher at a certain elevation and then decrease below that elevation because of the drainage. You might have zones of effectively perched water tables because of a layer of really low permeability tailings. And we might have pore pressures that are greater than hydrostatic, because that zone is still undergoing consolidation. So it hasn't reached equilibrium. So all of those things can seriously affect your calculations of these normalized parameters. Remember, we're going sigma v dashed. In order to know that, we calculate sigma v from bulk unit weight, but we need to know what the equilibrium pore pressure is. So we need them for interpretation, as I said. Pore pressure profiles are often non-hydrostatic. Dissipation tests don't take that long in most tailings, but you don't want to do them unnecessarily, certainly. And if you've got a functioning vibrating wire or other kind of piezometer network, it can kind of give you a reality check on what your equilibrium pore pressure is. And it affects these normalized parameters. So undrained strength, this is the equation that's commonly used. Again, it's not measuring it directly. It's been inferred from a calculation of this type. Corrected tip resistance minus your total vertical effective stress divided by some magic parameter, which is the empirical cone factor. Now, I really want to stress that in a lot of the early work looking at trying to get what is this factor that we use, people did very sophisticated plasticity analyses and got upper bound and lower bound values and so on, which said, really, you should expect it to be between about 11 and 19. Now, if the number you're using is outside of that, it might be plausible, but it's worth just thinking about where did that number come from? How did you get to this modified NKT factor? And we see significant abuse of field vein tests giving NKT factors which make no sense, but we see it again and again. So here it is. It's sometimes correlated with field vein tests, but big red alert here. Those vein tests themselves may not be fully undrained. So as you're rotating the vein, you're getting consolidation taking place, you're getting more resistance, so you think you're measuring an undrained strength of 200, but it's actually 120. You're saying, oh, this is my undrained strength, so therefore, from this CPT, this is what the undrained strength should have been, so now I can work out what my NKT is, right? All kind of reverse logic. But you need to make sure that your your field vein tests are truly fully undrained. So, NKT values of 32, it's like, maybe not. So how do we know whether it's drained or undrained? Okay, so in the CPT, the concept of the dimensionless velocity is crucial. And a lot of the really useful stuff that we use, and we still kind of mining, I think, to bring into the tailings industry, was generated by the offshore people, the people doing offshore foundations. And this is one example. So it says you take your actual velocity, that's that 20 millimeters a second. You've got your cone diameter, it's usually 35. And CV is the coefficient of consolidation. Now, the things we don't really know what that is in situ, but again, that can be inferred from dissipation tests. I'll show you in a second. And well, that's not really CV, it's kind of CH with a bit of CV, but it's a measure of consolidation, of the coefficient of consolidation. So this dimensionless velocity is crucially important. So this is data, we did a bunch of tests in the beam centrifuge at University of WA. So we created what we called an artificial tailings, just a mix of sand, silt, and kaolin. And the reason we did that is so that we can recreate that material whenever we want. Because the worst thing about some tailings work is you get a decent size of sample, you do a bunch of tests, and then you run out of the material. So you go back to site, go to the same place, but what you get is actually different. There's different PSDs, there's different this, different that. And then it screws up all your initial work, or it's hard to dovetail them. So we create this artificial tailings, just as an aside. So here we've got that normalized velocity on the horizontal axis. We've got the normalized tip resistance on the vertical. And you can see, well, depending on your velocity, you can get a range of numbers. So what are those numbers? Where are we? Well, from that equation, the left hand, that's the blue shaded area, your velocity is low enough that you're actually drained. You're doing a fully drained CPT test. The one on the right, you've got an undrained CPT, and in the middle, you've got partially drained. Right? And here, and it's not uncommon, you get a 10-fold difference. So just be really careful that if you're getting a large tip resistance, it doesn't mean that you necessarily are not contractive. This was a mistake made in Fundau. You'll also see there's, as I said, a 10-fold difference, and the undrained, there's a slight increase with velocity, the last 3 data points. There you're starting to get some kind of viscosity effect, I think. That's commonly recognized in vein tests as well. So in order to determine that undrained or drained, we need to get this coefficient of consolidation. This is probably the most commonly used method, Tay and Holsby, where you plot the pore pressure dissipation phase with time. You use that equation shown there where the A is actually the cone radius, not the diameter, so just be careful about that. And the I subscript R is a rigidity index type measurement. It's the shear wave velocity divided by undrained strength in this equation. And then for the solution by Tay and Holsby, the time factor T star is 2.245, I think it is. So you measure the T50, corresponding T's time factor is 0.245. You know everything else in that equation, hopefully. So you can get the CH, your coefficient of consolidation. So during the CPT testing, you can get a pretty good handle on what your likely CH is. So you can then check on our CPT tests, actually undrained or partially drained. So the thing I mentioned there is talked about the kind of correlations, is the vein shear test. It's pretty useful and pretty simple to use. It's well known. You're measuring the torque required to rotate that vein, and you assume you mobilize the strength on the vertical faces that the vein cuts, as well as the 2 horizontal surfaces, top and bottom. But again, this was developed solely or predominantly for clay-like materials, with a standard rate of rotation, whether you use 6 degrees a minute or whatever the applicable standard might be in different countries. That was for clays. So by rotating it at that standard rate, bingo, you get undrained shear strengths, which is great. But unfortunately, a lot of our tailings are far more permeable, far higher degrees of coefficients of consolidation. So you're doing a vein test, you're measuring a so-called undrained shear strength, but it's meaningless in that context, unfortunately. So then you have to ramp up the rate at which you do your vein test. And that then becomes quite a challenge, because a lot of contractors previously certainly were not geared to doing that. Now they're much better equipped. Now, the other thing I find perhaps something we should be moving away from is this practice of remolding the soil in the vein test. So here we've got the measured torque converted to a shear stress, degrees of rotation. You often get the peak at a fairly small rotation. Then it dies off, as you can see, it plateaus. And then what's fairly common is to then rotate at a much higher speed, probably more, even higher, much higher than that 0.6 degrees a second. Rotate 10 times, and then you make another measurement of resistance. That's your so-called residual. Well, it's not. I don't think it is. It's what you've done with the food mixer. It's that strength. It's completely remolded. So I think what's becoming more standard now is to keep rotating at a constant rotation rate, get your peak, and then monitor the post-peak behavior. But the trouble is, how do you know your peak strength is undrained? And something we've been working on recently, how do you know your remolded strength, or your large strain strength is undrained? And maybe we get a chance to talk about it, but try and shy away from the word residual, because residual, I think, is when you've got clay particles aligning in a certain direction after lots of shear. So it doesn't really apply to silty sand tailings. I prefer large strain strength. But anyway, here we've got some vein tests. So on the left is the ratio, the peak strength ratio, the undrained, of the sigma U or SU over sigma V naught dashed. And on the horizontal is time to failure. So here they've carried out tests at different rates of rotation. And depending on that, you actually get different strengths in the same material. Now, many years ago, Blight and then Dick Chandler in particular came up with a way to estimate, is your vein test drained or undrained? So equation you've kind of seen before in other guises, CV, time to failure, D squared, vein diameter, and so on. If that factor is greater than 0.05, then based on that work, you're actually likely to have partial drainage during shearing. So what can you do? Well, you can ramp up your time to failure. You can shear faster, right? So it's the drainage effect you have to take account of, but then if you start going faster and faster and you're in the undrained behavior, then you get this kind of viscosity effect. So it's shown here for the squares, that's the peak strength. The circles are the large strain strength, I prefer to call them. And you can see it's going up with the increasing rate of rotation. So then you're probably measuring something that you don't really want to know. You want to know the undrained strength at the lower velocities. But at least we can correct for that. So in terms of getting undrained shear strengths from the vein, can be affected by both drainage and rate. Once you've got a result, it's really hard to kind of disentangle the effects of consolidation and drainage. It's hard to correct for. So it's better to get it close to correct in the first place. Work out what rate of rotation you need, and then do that. Now, a lot of the new the vein equipment people have got the drives right at the base of the hole, or just ahead of the vein. You're not trying to turn it from the surface and getting all those kind of twisting effects. So it's possible to do rotations. Some people are doing, I think, 720 degrees a minute, really fast rates to get undrained. In terms of the viscosity, we can correct for that. That previous slide showed you get this kind of linear increase in strength. So you want to go fast, but not too fast, if you can help it. So that's it. You can get, if you're trying to measure undrained strengths with the CPT, make sure it's undrained. Showing you a couple of ways to do that, but also if you're going to then try and correlate with vein tests, make damn sure the vein tests are undrained. And then just finally, and briefly, because this is a whole postgraduate course on its own probably, is using these full flow penetrometers. So they're shown on the right there. You see the CPT at the top, you've got the ball penetrometer and the T-bar. Now the reason these were developed is mainly for soft soils. At the bottom of a seabed, even though you might be under 200 meters of water, the bed is likely to be normally consolidated. Really low shear strength, even under 200 meters of seawater. So they wanted to measure undrained strengths in very low strength materials. With these devices, as you're pushing them in, the soil essentially flows around them, hence the full flow term, whereas the cone, it's sliding up the outside. So with these devices, and they were able to do these plasticity solutions again, which narrowed that the boundary from 11 to 19, as it was with the CPT, to a much narrower theoretical range. Now, I say theoretical because it depends on the roughness of the ball and a few other things, but you've got a much larger area as you're pushing, so it's accurate in soft soils. It's less affected by overburden. It's less affected by pore pressure measurements. So we're seeing this trialed in a few TSFs in Australia. I think I might have some data later on in the course. It's not appropriate for stiff materials. We tried this once, and we managed to snap the rod because we were trying to push it into red muds, which are desiccated, and it kind of deflected the cone. You can also end up, you push the ball in and you try and do cyclic tests. Because it's stiff, the hole stays open. You don't get the full flow. So, it's got certain applications, softer, lower undrained strength materials. But as I said, you can also get a really good estimate of large strain strengths. If you do the penetration tests, then you pull it back up again, push back in, and you do a kind of a cyclic test until you get a constant large strain strength. So I think we're going to see more of these apparatuses in select types of soils. And then, of course, it's always good to have more than one type of set of data. So here we've got a ball penetrometer, we've got shear veins done at the right speed to get a peak, and we've also done a few direct simple shear tests in the lab. So the more kind of data that you can use to confirm one set of in situ data, the better. So just some concluding comments then. It can be used to estimate undrained shear strength, I think with some confidence and some repeatability. But if you're measuring undrained strength, it's got to be undrained. Sounds pretty obvious, doesn't it? But be surprised how seldom that's the case. Dissipation tests are essential. The vein can again be used, but it was developed for clay so that make sure that you then up the speed as appropriate. And I think these full flow penetrometers providing an alternative, but for a limited range of materials. So I think that's all I'll have for now. Thank you.
Thanks, Andy. Yeah, thanks very much, Andy. We really appreciate that. There's some guidance and warnings coming through, and not just from Andy's presentation, but also from Louise's presentation about understanding what you're measuring and then making the interpretations correctly. Right, we're going to move on then to SW Jacobsz' presentation. SW Jacobsz is based at University of Pretoria, and he's been doing some quite interesting sampling and testing, and he's going to talk to us about undisturbed sampling. And he was hoping to get the University of Pretoria Anglo-American mobile testing unit here for us to have a look at. It hasn't worked out because it's busy in the field, but over to you, and you can explain to us what happens in that mobile lab.
Thank you, Andrew. Good morning, ladies and gentlemen. Thank you very much to the organizers for the opportunity. So I'm going to talk about, we've heard from Andy now about in-situ testing, doing cone penetrometer testing to measure in situ what happens in the ground, but quite often we like to take a sample out and then test that in our laboratory. So I added a second slide to indicate can we really do undisturbed sampling. So I'm going to talk about that. Why would we, first of all, the content of my presentation is to talk about some aspects of sampling. We are changing the stress state in the soil when we sample. When we do that to a sample, what is the effect? Then what is the effect of sample disturbance? We can densify a sample, and that affects shear strength. It also affects the way in which a sample fails. So then what can we do to minimize sample disturbance? So I'll briefly talk about the mobile lab that we are running that Andrew spoke about. And then we recently also started playing around with flash freezing of samples using liquid nitrogen, and I will explain about that and then present some conclusions. So why would we like to sample tailings? And as I said, we don't always test in situ. Sometimes we like to take a sample to the laboratory and characterize the properties there. So we need to get it out. And this slide summarizes the challenge that we are sitting with. I want you to focus especially on the plot on the right-hand side, where we are plotting the stress path in QP space for samples of slightly different state or friction, void ratios. This gold tailings, and you can see that if we share a sample with a void ratio of 0.69, you measure a high undrained shear strength. If you reduce that void ratio slightly, increase the void ratio slightly to 0.72, you have halved the shear strength. And then a 0.02 change in that void ratio again, and you cut it down by another 50% or so. And then a 0.01 change in the void ratio again would affect your undrained shear strength by another 50% or so. from the value that we measured. So there's extreme sensitivity in the undrained shear strength of soils when we are playing around with the void ratio. Extreme sensitivity. And so what can we do to sample? There are broadly two ways which are used a lot, and the one is block sampling. If you can take a nice block of intact material out of the ground. It is not possible to do that if you have a very soft, weak sample. Why do we sample tailings dams? Because often we have some really soft and weak samples that we want to take out of the ground and go and characterize in our laboratory. And unfortunately, we cannot get block samples of such material. So we have to resort to some other means of sampling, like borehole sampling, where we drill a borehole down to a certain depth and then extract using hopefully a nice new modern sampling technique, intact and hopefully undisturbed sample. I want to show this slide just to talk about the principle of removing a sample from the ground. So if you take a sample out of the ground, you are going to take all the stress off the sample. If you are dealing with a clay material and you take the sample out of the ground in that sample responds by generating very large suctions are generated inside to allow for or compensate for the amount of stress that you have removed. So the net effect is, if you are working in a clay material, you have not disturbed the effective stress. But in a material which is more pervious than clays, so in silts and sands, when you take the sample out of the ground, you cannot get that response in the negative pore pressure because the material is too pervious. And it will simply drain, not generating those negative pore pressures. And the consequence is that you are changing the effective stress. If you are changing the effective stress state, you are quite likely shearing the sample. So we sit with an enormous challenge in sampling anything other than clays. The activities that we typically encounter when we have to sample using a borehole drilling technique will be, we are drilling to a certain depth. Hopefully it will be something that is not shaking the entire world around you up too much, but that may cause a little bit of densification of the sample, which is still underneath the bottom of the borehole. Then we are going to drive a sample tube into the ground and invariably shear that sample. We are then going to pull on that sample and hope that the sample comes along, and then we'll transport it to a laboratory. So with all of those actions, there are big stress changes associated, and quite often also quite a lot of densification. Then when you arrive in the laboratory, the sample needs to be extruded from the tube. We need to place it in the triaxial. There's sometimes some trimming involved. We need to saturate the sample. We need to then consolidate the sample. And only then are we going to start loading the sample. And you can just imagine the changes that that sample has gone through up to that point in time. So to get that 0.01 change in void ratio is really likely, really, really likely from what we are doing to the sample. So I'm not quite sure why some of these things moved a little bit, but what I want to talk about is we are typically modeling really, really soft samples or trying to sample really soft samples. And we are going to change the effective stress state in those samples, and we are going to disturb them. And the way in which we disturb them typically densifies them, which means that we are overestimating their strength. And also their ductility may be affected in what we are doing. So this is some work of one of my students, Greg McDonald, to try to look through a window what happens to tailings when you sample it. You can see on the right-hand side that we are pushing a sample tube that we split along its length into the soil. And you can see that the top surface inside the sample is a bit less than the top surface outside the sample. This is a soft tailings sample, and it means that we densified it. You can also see there's a little bit of supernatant water standing on top of the sample in the tube. So we have caused a little bit of contraction of that sample, and we have obviously changed the void ratio. If you look at the plot that is shown there, in the ground we buried some pore pressure sensors, and you can see that when the probe advanced or the sample tube advanced towards the sample, we generated up to about 15 or so kilopascal of water pressure. And then when the sample was extracted again, we induced a certain amount of negative water pressure. So we must have changed the effective stress by at least about 30 kilopascal by just getting the sample tube into the ground and pulling the sample out. So what I want to do then is to think about stress state in the ground, then inserting a sample, pulling the sample out, and what happens to the stress state when we then extrude it, and then we want to ideally reload it to the stress state in the ground and then shear the sample. And so the point that it's a pity I don't have a pointer to light on or point on the screen, but the dark blue circle which says initial state is what we guess the initial stress state to look like. We can usually guess the vertical stress in the soil quite accurately from self-weight and the depth where we are, but we are very uncertain about the horizontal stress. So we have to make some kind of a stab as to what the value of K0 would be. That concerns or affects the size of the Moore circle. So that blue or dark blue intact circle, not the one with the dotted line, represents the stress state in the ground. Then we drive the sample, which may cause dilation or contraction of the sample, and it will temporarily impose that yellow Moore circle. So it could also be to the other side of the sample. Then we pull the sample out, and it gives us the little green Moore circle closer to the middle of the slide. And then when we get to our laboratory, we extrude the sample and take nearly all stress off, and that brings us very close to, or you can see that little blue Moore circle very close to the origin. That sample was subjected to a certain K0 value. Then we took all stress off, and that sample is now feeling a horizontal stress and a vertical stress are very close to 0. So you may argue a K0 value of about 1. So changing those Moore circles imposed a certain amount of shear the sample. When it is sitting at that stress state very close to the origin, it is very, very prone to be damaged, because you can imagine a small amount of load that you can apply to the vertical or the horizontal stress on the sample will very quickly enlarge that Moore circle to violate the failure criterion, and you will plastically deform the sample. So if you manage not to do that, you can then raise your cell pressure, take the sample back to a stress state where we thought it would have been, and we thought it was going to be at the dotted circle that I showed. Now, on purpose, did not draw it to be exactly the same as the first one, because we do not know K0. And what you can see, if you look at the apex of that circle, there's a stress coordinate. That was the stress coordinate in ST stress space. And that is different from where it was before. So you can see in this case, it's a bit further from the critical state line than where we were before. And we are now going to start shearing that sample. And depending on where you start to shear it, above the floor of this graph, basically, is going to affect the brittleness very, very substantially. So Prof. Andy is going to talk about brittleness in one of his presentations soon, but it is represented by that graph that moved a little bit on the bottom left of the slide, where we get peaky behavior. So if you, depending on where you start to shear a sample, you may get different behavior. I'm going to skip this slide and show this one. So looking at the little graph with to illustrate peaky behavior, I want to now consider the stress state in the ground and the effect that that has if you have a material that is potentially strain softening. So we would typically know the normal stress in the ground, or the vertical stress in the ground. And you will have to make an estimate about what the K0 value will be. And if you do that, depending on your guess of K0, you may sit at various stress states that could be substantially different. And now I really want to point to the screen. So you can see if we guessed K0 to be equal to 1, we would have had a stress state there. As you start reducing K0, the values went to 0.8, 0.5, and ultimately close to 0.3 there. So without doing anything to the soil, but just varying K0, you are bringing the stress state very close to the failure envelope. What happens in terms of the state parameter at the bottom? So if you have a high K0 value, you have a high stress level in the ground, and the stress level may be a substantial distance elevated above the critical state line, and you have a big state parameter. So as you lower the K0 value, you move closer to the critical state line, reducing the state parameter. But you are imposing an enormous amount of shear in that sample. So what is the difference in behavior between samples that have a high or a low K0? If you have a high K0 value, so close to 1, you start at the floor here basically, and when you shear the sample, it will go up, it will go reach the peak, and only then behave prettily. So you have a lot of scope to take a trigger to initiate a liquefaction. If you have already imposed a large amount of shear in the ground, as shown by the dot that I'm pointing at there, you need a very small trigger to take you over the top and induce liquefaction. So we should not only worry about the state parameter, but the in-situ stress state is also crucially important, and that is something that is hardly ever measured. And then I want to show some work that Yashay Naransamy, my PhD student, who recently submitted his work, did. This is a tailings dam on the East Rand, where we try to physically monitor the in-situ stress state. You can criticize stress measurements in soil very, very severely, but I do not have time to defend what we have done, but it can be defended under certain conditions. So we buried stress stations in the ground that looked like the following. So there were stress cells that could measure horizontal and vertical stress. In addition to that, we had 2 tensiometers at every location that could measure both positive and negative water pressure. And there was a volumetric water content probe that would allow us to measure the moisture content in the ground, basically. And these were then regularly logged, and they were buried by slurrying them into a shallow excavation. So at least when that slurry was deposited, you had hydrostatic conditions in the vertical and horizontal direction. So at least initially, we should have measured correctly. So you can criticize stress measurement, as I said before, but I want to show you the data. So this is just our instrumentation locations after they had been buried, and you can see some data loggers standing there sending us the data remotely to Pretoria. So these are vertical and horizontal stress measurements at different locations. The dark lines are the vertical stresses, the light colored lines are the horizontal stresses, and the black dots represent the vertical stress calculated from self-weight that we know. So you can see that there's good correspondence between the horizontal the vertical measured stress and the estimated stress. So with these stress, these are total stress measurements. One thing that happened is shortly after our installation, they decided to step in the wall, and you can see that brownish color leveled off, the stress level leveled off because they stepped in the wall, and that was not in the slope, or not in an area where the slope was growing anymore. Then these are the pore pressures from the tensiometers. So every one of those instrumentation positions have 2 tensiometers, and you can see the readings represented by a light and a dark colored line. And you can see excellent correspondence between those 2 suction measurements, which give us confidence in the suction measurements. There's also a rainfall record indicated at the bottom. But what you can see is very soon, we start to move into the realm of negative pore pressures, and we don't ever go to positive pore pressures again in this area. This installation is still being monitored. The data that I'm showing you there is up to about, I think, a week or 2 weeks ago. So we are continuing to monitor that. It will be very interesting to see how that develops as the dam gains further height. So with the pore pressures and the total stress is known, we can estimate using an appropriate method the effective stress, and that allows us to plot K0, and that is what we are really interested in. So from the instrumentation that we have in the ground, we can we observe a K0 value of about 0.5. So it is very likely that your horizontal stress measurement is underestimating the true stress state. So we can say at least that K0 is going to be above 0.5. It is going to be 0.5 or higher. But at least we have some confidence now in where the stress state in the ground lies. So that is valuable because this greatly affects the brittleness of our soil. What I want to do then is to look at, I just want to stop this for a second. If we now know the stress state in the ground, there's another important factor, and how that is the state parameter. How does that affect the way in which a slope can fail? So this is in our geotechnical centrifuge where we prepared a soil slope at a dense state, and we allowed the water table to rise, and we wanted to observe how it failed. So you can see that the water table is rising, and then when it touches the toe, we start to get sloughing at the toe, propagating backwards, and the soil goes and lie at an angle that you can calculate for flow parallel to a sloping surface, but never do we get a very dramatic failure. Then we did exactly the same experiment with a loose soil, so a positive state parameter. Rising water table, you can see over there, nothing happens to that slope except for a bit of densification until we touch the toe, and instantaneously at 30 Gs that failed. So I wanted to show you a bit slower. So this is now played back at a quarter of the speed. And you can see that if your state parameter is high, your failure mode is very much different compared to a state parameter which is negative or in the dilatant state. So really important for us to understand the state parameter. So what I want to do then is, I do apologize that these things managed to move in the migration from Pretoria to Joburg. But what I want to look at is on which, I showed the bunch of activities on the left-hand side that we do during sampling and potential mitigating measures on the right-hand side. So I am going to focus only on 3 of them. What mitigation can we do? The one is testing on-site instead of transporting a sample hundreds of kilometers potentially to a laboratory. And the other one is when you do extrude a very weak sample, can we test that on-site by maybe flash freezing it and then extruding it so that it does not slump? If you extrude a weak sample, it typically slumps, changes the void ratio, and what happens if we flash freeze it? So I want to show some of those results. So we've got, in collaboration with Anglo-American, a mobile soils laboratory set up, and the intention is that we avoid or minimize the disturbance associated with sample transport. And this is what it looks like. So it's an 8-ton truck, and it is fully equipped with solar panels on the roof, a battery system. There's a generator and ability also to plug into the mains if there is power available. There's an aircon system to maintain constant temperature and security and tracking and lighting systems and the rest that we need in this country. And then the equipment that we've got inside is 2 standard triaxials, then also 2 triaxials with bender elements and local strain measurement. And then we are fortunate to have 2 dynamic cyclic simple shear apparatus. All the equipment that I mentioned from GDS, and then there's your standard deaerator, drying ovens, a freezer so that you could do sample freezing. And we also have a dew point hygrometer and an automated odometer available that we don't always keep in the lab, but which we can place there. So with a triaxial, this is just one of the triaxials set up in the laboratory. You obviously test in triaxial compression, and then the DSS, or the direct simple shear apparatus, for those who are not familiar, allows you to shear a sample in near perfect shear. So it's a big improvement on the old traditional shear box. It costs probably 100 times more than an old traditional shear box, but it has a bunch of advantages that we can talk about, but not today. So the big question that you would like me to show you is, what is the comparison between testing a sample on site and then one that we have driven to Pretoria? Now, sadly, we are not able to present that result yet today, because at the moment we are really scrambling to assist Anglo to show compliance to the GISTM standard. So in the new year, we hope to be able to do that work. But what I would like to show you is some of the work that we are doing in terms of flash freezing. So this is our first trial. We've got a sample that you can see on the right-hand side, a sample tube that we are going to lower into a pot of liquid nitrogen to flash freeze it to minus 150 odd degrees centigrade, which very, very rapidly freezes it rock hard, and then it can easily be extracted. So we usually cut a slot in the Dames-Moore sample tube. This is not a Dames-Moore sample tube. Then it can be extruded, and it is much more forgiving in terms of handling compared to a sample that you extrude from in an unfrozen state. So that is the process. It was a big mission to convince the mines that this is not a very hazardous operation. And so this is in our laboratory in Pretoria. And you can see that despite a bit of bubbling and so on, it can be done safely. So I'm convinced that it can be done safely. And when that sample comes out, it is really easy to handle, of course. So what we would do is place it in the triaxial, apply confining stress of about 50 kPa, thaw it slowly over a bunch of hours, and then go through the saturation process. So I want to show just a comparison between the results. It's platinum tailings, where we froze some samples and we had a bunch of samples that were not frozen. And so the way in which these samples were recovered is by means of Dames and Moore sampling. So I've spoken to the drilling contractor, really important that you speak to the drilling contractor, and he said to me they would push the sample tube into the ground, and then they would wait for dissipation to take place, and then they will sometimes wait for an hour, sometimes 2 hours eventually, and then they would pull the sample tube back up. And he said then they would put caps on and everything and then store the sample. But quite often the sample would drop out and then they would try another location. The samples that dropped out are the samples that we want. So what we have seen here is you can see that all our samples, without a single exception, and we've done about, there are 33 stress paths shown there, all of them, many of them contracted a little bit. Some of them contracted even beyond the point of the instability locus when you get to the apex of the stress path and it goes down. We call that the instability point. So some of them went even beyond that point, but eventually all of them turned around. So we did not see a single sample that contracted. Does that mean that the soil does not contract? It certainly does not, because the samples that dropped out could not be tested. And I think they are the samples that we are really interested in. So our nemesis and our serious challenge is still how to get those materials out of the ground to be able to test those. So the benefit of having a mobile lab is secondary to this. I think the disturbance associated with transporting these samples anywhere is much smaller than the massive amount of deformation that you can cause. I showed that photo earlier where the level of the tailings inside the sampler was lower than outside. So that is our problem, not transporting the sample elsewhere. But what I've done is I've taken all the samples that contracted to a apex and then went a little bit beyond. Some of them were frozen, some of them were non-frozen. And we do not see any significant difference between the two. So the one big thing that we need to answer is, do we change the properties of the soils by freezing them? And visually comparing these two, there's not a dramatic, obvious difference between the two, but this is only the very first study that we have done on this material. And the master student that we have recruited is only starting in the new year, where we will do this in a very nicely structured way, preparing samples to exactly known void ratios, freezing some and not freezing some, and compare the results. But just based on preliminary indications from a platinum mine, there does not seem to be a massive difference between those two. So, yeah, the observations, I think I discussed most of the observations. The slide is there for people who want to read it afterwards. The bottom line is, the samples that we're really interested to get out, we could not. And that is a problem. That is a severe challenge for all of us. And then I just want to conclude. So sampling disturbance affects the void ratio of the material. And if we affect the void ratio, we change very important material properties. We change the strength of the soil. We make it stronger than what it should be. We also change the mode of failure from something which should be really brittle to something which is more forgiving. So sampling in anything other than clay is a challenge, because you are going to change that effective stress state. The very act of pulling the sampler out, or the sample out of the ground, induces an amount of shear, an amount of densification. And in situ stress state, that point that I want to make is that in situ stress is probably not isotropic. And if it is not isotropic, how close is it to our instability locus or our critical state line? So it is important that we do not only worry about the state parameter, but also worry about the K0 value, so the in-situ stress ratio. Then I presented the two measures that we are attempting to work on in terms of minimizing sample disturbance, so it's the mobile lab and the flash freezing. Still early days, so greatest challenge still remains to pull that sample out of the ground. So I'm sorry that I could not bring the mobile lab here today. So unfortunately that is testing at the moment, but hopefully there will be an opportunity to show that around to people. And if you are interested to get a little bit more of the basic theory explained in terms which is just someone else's voice compared to what we are hearing here. We've got a tailings course at the University of Pretoria next week, running on Monday. So those interested to attend that can speak to me as well. Thank you very much for your attention.
Thanks very much, SW. I think, again, we've been challenged in terms of how do we get this right. We're in an interesting industry right now in terms of getting all the testing done correctly and getting important information. So Andy's going to continue with us now on undisturbed sampling and testing. We're slightly ahead of time, so if Andy finishes ahead of time, we'll probably have a few questions before lunch. So there's an opportunity for you to just think about maybe some questions before we go to lunch. So over to you, Andy.
All right, me again. One thing SW mentioned, I think, is really important. At the moment, to be working in tailings is really challenging, but with incredible opportunities. So if I think back, like 20 years ago, people were designing a tailings dam based on 3 SPTs and 1 triaxial, and that was it. And I think that like the sort of standard in the conventional geotechnical engineering foundations, retaining walls, and all of that was up here, and tailings was like down here. I don't think they've moved a hell of a lot, but I think tailings is like up here. I mean, we're doing hollow cylinder tests, we're doing full flow penetrometers. We've got now probably one of the best equipped geotechnical laboratories in the world, all through getting industry involvement in tailings testing. So there's so many interesting things. We're working on ways to measure in situ volumetric water content using nuclear magnetic resonance imaging. I mean, could you have conceived of that 5 years ago? So it really is a really interesting field, and I think there's a lot more still to come. So watch this space. All right, so a couple of thoughts on undisturbed sampling and testing to pick up from what SW was saying. I think one of the things to ask yourself is, what am I actually trying to measure? Too often, I think we do something because it was done before. What aspect of the soil behavior are you really interested in? Is it the state parameter? And in fact, do you want to just know that you're in the contractive region, or you're safely in the dilative region? Is that in itself sufficient, perhaps? Or do you want to measure strength? We can do in situ tests that I mentioned before, but you probably want to back that up, maybe with some laboratory. But the 2 bottom ones are probably the ones that are really challenging us now, particularly when we want to start getting into reasonably competent numerical modeling, where we want to know what is the stress-strain behavior, and in particular, what is brittleness. And we'll talk about what brittleness means. Some actual quantification perhaps a bit later on. But basically, it's after peak strength, what happens, and how fast does that happen? But which of those are you trying to measure? All of them? If yes, why? Do you really need that? So because I think some of them, as has already been alluded to, are much more difficult to do kind of consistently and in fact reliably. So estimating state, then that's this. You've seen it before. It's how far away in void ratio space are you from the critical state line? In terms of estimating state, particularly with more cohesive plastic-like materials, we can usually get pretty good undisturbed samples using thin-walled piston tubes type sampling. Much more difficult, as we've seen already, with cohesionless tailings, silty sand tailings, sandy tailings, etc. It's a real challenge to get that. Because we disturb the tube samples, what we get back in the laboratories change the density, void ratio, etc. But there may be a way around this to some extent. So what we've been trying to encourage the consultants to do, and we've worked with a couple of the big projects in Australia, is to take the sample, try and make sure it's completely sealed on extraction. When you take it back to the laboratory, you might then extrude it, and you can see in that extrusion tray, that's what the sample looks like. Okay. Clearly, it's not in the same state it was, for all the reasons already mentioned. There's some free water there that's separated out. During the penetration, you've actually compressed it perhaps, released water, maybe during the transport, whatever. Now, how do we do something meaningful with a sample that looks like that? You can remold it. Remolding, I mean, you can reconstitute it in the laboratory using one of the methods Louis mentioned, moist tamping, slurry deposition, perhaps, but what is your target void ratio? I might digress here for a second, but when we were looking at the failure of the Maritzburg Tailings Dam, which happened in 1994, and George Papageorgia, I think some of you might know him, was doing his PhD at Wits on that, and we were starting to come up with suggestion that in fact that material could have been contractive. But the opposition we kind of got was quite extraordinary. People said, everybody knows gold tailings dilate, full stop. When you dug down a bit, the reason that they were saying that is because lab tests were reconstituted by a little bit of compaction, a little bit of densification. Otherwise, the samples didn't stand up. They fell over. So people were making it dilative in order to test the strength without thinking through all this critical state stuff. And that was prior to the Jeffries and Bean book, and et cetera, et cetera. So if you're going to do reconstituted samples, you want to try and get to a void ratio that is similar to what you think is in the field. But how to get there with less cohesive materials? Well, try and get as much of the water as you can. Accept the fact that you've disturbed it, but really, if you think about it, if you can capture all the water from the sample, you can get a pretty good estimated void ratio, as long as it's from below the phreatic surface. Because what is it? Void ratio equals water content times specific gravity. So if you can get the water content, you can get the void ratio. A pretty good estimate in many cases. So if it's fully saturated, you might still be able to determine void ratio. And if you just want to know, am I above or below the critical state line, this may be sufficient. I think it's probably not, because the further you are from that critical state line, the more brittle you are probably going to be as well. But again, if you're not doing numerical modeling, well, then maybe it doesn't matter. Now we suggest firstly, don't dry it all in a 100-degree oven, because you then change the character of the material, perhaps. You might change some of the kind of aspects of the fines in material. In particular, you might make the SG cause some effect on the specific gravity. So what we suggest is that you dry it in a 50-degree oven, then so you get an initial estimate of water content, but it's not quite the final. Then you mix it thoroughly, and you can then subsample for index testing, for GS, because you want to know the specific gravity at that location, if you want to use that simple E equals WG calculation. Then you can dry it thoroughly and back calculate the original gravimetric water content through that two-phase drying. And then you can get an estimate of void ratio and dry density, whatever. So that, if it works, if you can get the sample where you recover everything, it at least provides a good target for remolding or reconstituted samples, but it also gives you an estimate of state. So here's an example. So the left was a CPT profile where we did the interpretation based on the Plews method, and again, accepting that it has it's not an absolute measure, but it's clearly contractive, I think, the conclusion you would come to there. But when we then plotted those gravimetric water contents converted to void ratios, compared them with that critical state line shown there, that those two data points, the two squares that happens to be a green line, they were way above the critical state line, clearly positive state parameters. So if that's what you're interested in, then it may it may be feasible even for some of the more problematic materials. But if you wanted to get those other parameters, the brittleness, the stress strain curve, well, that is definitely much more of a challenge. Now, before I talk about that a little bit, I wanted to just go through this approach. Maybe some of you are totally familiar with it, but in SANCOLD, so that's the Australian National Commission, obviously on large dams, in their guidelines 2012, which are then updated in 2019, and incidentally currently going through an excruciating update process. But they mentioned, or that document mentions that you can perhaps get good estimates of the undrained strength analysis or the undrained strength ratio using this approach called the SANCOLD. So for those of you not familiar with it, I'll step through it really quickly. But again, this doesn't work for cohesionless silty sand tailings, for very brittle tailings, etc., and we'll show why as well. So the crux of the SANCOLD approach is that your critical state line, the lower one, your normal consolidation line, isotropic or 1D, stay a constant distance apart. They offset by that arrowed vertical line shown there. And when you unload from the normal consolidation line, you get that very stiff response, very small change in void ratio. But if you reload, obviously it goes back onto the normal consolidation line. Right? But now let's think about what SANCOLD suggests is possible. So maybe we normally consolidated, you've got K0 of 0.5, 0.6 or whatever. You're sitting on that normal consolidation line, 1D. When you sample, take a sample from below the phreatic surface, so it's fully saturated. You get that first upper dashed line, you're unloading, as we've seen already. Then maybe during handling, transport, etc., you get some additional disturbance, so the void ratio decreases further. And then if you reload back to the estimated in-situ stress, and again estimated because you have to have a stab at the K0 value, you get to that point shown by the open black circle. Same mean effective stress, same vertical effective stress, void ratio is different. So in fact, if you reconstitute it back in the lab to the same vertical effective stress, you're actually testing a denser sample than was in the field. But if you then just continue loading it, it will eventually converge onto the normal consolidation line. If there's a unique normal consolidation line. And this is where things get messy again. We'll talk about this a bit later on. That for a lot of cohesionless silty sand type tailings, there isn't a unique normal consolidation line. Sometimes there is, sometimes there isn't. You get what's called transitional soils. And unfortunately, people use this word transitional to mean about 3 different things. What I'm talking about here is a non-unique normal consolidation line. For most clay-type materials, it is pretty much unique. So if you then continue loading, you get that dark dashed line, and it eventually rejoins the normal consolidation line. Maybe twice the initial vertical effective stress. The benefit with that is that if you do that in the lab, you can then get realistic undrained strength over vertical effective stress ratios, or undrained strength over mean effective stress. So you actually can recover that kind of aspect of the behavior. So that's where the SANCOLD works with clay-like tailings. But you've got to be really careful. It's developed for clays. Our tailings can be anything from very clay-like to completely non-cohesive. And I think we don't know yet where that cutoff is. At what value of, let's say, plasticity index can we use SANCOLD confidently, and below which we should avoid it. And particularly if your critical state line is not parallel to your normal consolidation lines, or if the latter are curved, etc., then it becomes problematic. And here's an example. So you've got the normal consolidation line being curved. You do the same kind of sampling, reconstituting, but maybe it never rejoins that normal consolidation line, at least in the stresses that are accessible in the laboratory. So you might have non-parallel lines, you might have a range of potential normal consolidation lines, you might get dilative type behavior, so the chance-up approach is clearly limited to certain conditions. One thing I want to mention without really going through it in any detail, and I'm not sure to what extent it's an issue in South Africa anymore, but in Australia, Western Australia in particular, in the goldfields region and where the nickel mines are and so on, we often have hypersaline groundwater, which is used in processing. By hypersaline, I mean like 4 times saltier than seawater. Until I got there, I didn't realize you could get saltier than seawater, but that certainly is like 4 times as salty. So the problem is when you do your water content measurements, remember you're putting it in an oven, you're drying it overnight, and then you're measuring the change in mass, and you're taking the mass of the solid as what's left in the tray. But what's happened is during the drying process, all the salt precipitates. So you're measuring it as solid, where it's actually part of the liquid phase, because that salt is dissolved in the field. So there are corrections for doing that. And it can be very significant if you've got saline water, even as like seawater type saline, because you completely incorrectly estimate your void ratio, dry density, etc., etc. So there are techniques for doing that. If you want more information, you can speak to me a bit later on. But I just thought it's worth putting that in, having talked about the Shansip method. Other things that we think are now starting to get some focus is this effect of layering. We saw some kind of micro layering in some of the photographs earlier, but you can get it, bigger spacings than that. Occasionally, you get a sample that is relatively consistent. So even though that curve might show a big variation in the percentage that's finer than 38 microns, if you look at the numbers on that horizontal axis, you can see it's not that big a range. It's a fairly consistent type samples, but there is still differences. So we took intact samples and then trimmed them from blocks of that material, and most of them tended towards the critical state line, but again, that was then taken from blending all those samples. So you're taking kind of a composite. Does it actually represent those individual layers? Well, it wasn't too divergent here, but when you start looking at stress-strain response and comparing good quality block samples with reconstituted samples, you can see the stress-strain curves are all over the place. The brittleness, post-peak behavior is completely different, and you don't have to dig too far into the literature to find the same thing. So there, the solid lines tend to be the block samples, the dashed lines, samples reconstituted in some way. So a block sample is something that's possible to take near surface, but it's really, really not feasible at depth. And often that's where your problematic materials might be, as shown by an initial CPT screening test. So again, depending on what you're trying to get from your undisturbed samples, in cohesionless, silty, sandy type tailings, state parameter might be achievable, but this actual stress-strain behavior and all that goes with it is really an enduring challenge. And I think we've heard about that. So, just wrapping up, I think, ask yourself, why do you want to recover undisturbed samples? What is it you're trying to measure? Clearly, you can get better samples with clay materials. You might be able to apply the Shansip approach, but it's not amenable to the whole range. And stiffness and brittleness, and particularly the latter, I think at present not amenable to determination by undisturbed sampling in cohesionless loose tailings. I think we're actually destroying the very thing we're trying to measure. And you'll see a bit later on today, tomorrow, that when you do a K0 consolidated test, anisotropically consolidated triaxial test, when you then shear it in triaxial compression, the amount of strain that you require to get to peak strength and go beyond is kind of often of the order of 0.2% axial strain. Now, there's no doubt that we're imposing more strain than that when we're sampling. And there's a paper from mid-1980s, I think by Merson Belig, called the strain path method, where he shows exactly that. And in fact, talking to people subsequently, they reckon that's an underestimate of the strain imposed during sampling. So, as SW has already said, I think it's a real challenge, this. One of the things you might want to look up is the work that was done in Canada about 15 years ago now, called the CANLEX project, Canadian Liquefaction Experiment, where they froze the tailings in situ using liquid nitrogen. And then they cored out the samples and tested them in the laboratory, trying to get undisturbed samples. And that was a huge challenge. And of course, less of a challenge where the temperature is already minus 20 degrees than it is here when the temperature is plus 30, right? So freezing the ground is going to be a significant challenge. So I think let's be aware of that. We can be actually destroying the very thing that we're trying to measure with some of these tailings. And I think that's it. So I don't know if we've got a few minutes, Andrew, if you want to break for lunch now.